Right. Okay. So in our LMS page, so I have uploaded all the previous videos, and so videos are uploaded to YouTube, and the links are shared on LMS. You can check them, and then the lecture notes are there. So I will upload. So lecture 4 will be discussed next week, so I'll upload that later. And then within this week, I will upload the audio production techniques first assignment. So it will be a very, very simple project involved in like recording some sounds, and then recording multiple sounds and mixing them together to make a one video, compressed video for audio, for example, MP3, or so there are some other compressed versions. So it would be very simple project, but so I will give you marks based on how the work that you have done, or the effort that you have put on that project, right? So I'm not checking whether the final output is very nice or beautiful audio. Rather than that, so I will check the things that you have done, like the experimental work that you have put on the project. Right? That's what I expect. Huh? So, so when you are doing the projects, always try to do experiments. Always try to use the tools available, right? Then check what you can do with those, right? So from this module, so we are not expecting you to make very beautiful music or anything, but just to be familiar with these concepts and the how those concepts can be implemented using the tools available in this software, right? So those two things are our expectations. So if you see the learning outcomes, so it is there, right? But using them, by using them, if you can create very beautiful, very creative things, so that's that's something beyond our expectation. So that would be nice, but at least you have to play with the things, these tools, right? So that's the main thing, right? Okay, so let's okay. Right, so we talked about audio and So audio is electrical energy. So sound, and then if we convert that sound into electrical energy, right? So that would be audio, right? When sound is represented electrically, so that is what audio is. So we can represent like sound electrically in two ways, analog and digital, right? So before the computing technology was established and then popular, so we had audio in the analog form. So then now we have digital audio, like that's the famous, that's the mainstream, right? So in this module, we talked about digital audio, so mainly, right? So this is the evolution as we talked, and then digital audio. So in digital audio, we represent samples, right? Right. That means the continuous audio signal is represented using discrete samples, right? At several points, we take samples, the amplitude, the value of amplitude. So basically, as I told you last week, digital audio, or if we take a wave file, digital audio, so it is just an array, a set of values, right, with the time, right? So we have analog to digital converter and the vice versa. So that means digital to analog converters, right? Then in sampling, so what we do is, so in analog to digital converter, so we do several things: sampling, quantizing, and then encoding. So sampling is, so we select samples, right? So based on the time axis, right? So then in quantizing, so we select several values in amplitude axis, right? And then we cannot represent exact value of analog signals, so we have to limit them in two ways, like in samplings and then in quantizing. So we have to limit the analog representation when it comes to the digital representation. Okay, so and so finally in encoding we get a binary stream. So this is how it is represented in digital paradigm. Signal එක මේ විදිහට කලින් තිබ්බ එක binary stream එකක් විදිහට තමයි මේ computer එකේදී මේ computer එකේ හරි මොකක් හරි digital device එකේදී represent වෙන්නේ. Right? So sampling, we talked about sampling rates. Sampling rate is the number of samples per second. So usually the most so famous sampling rate is So if we take, so here the CD rate, right? 44,100. So that's the sampling rate used in CDs. If we take the last one, 48,000, so that it is used in DVDs and most of the videos, right? So if you are making, if you are doing a video, YouTube video, for example, so if you are creating sound for that video, so then the last one, 48,000 would be a good option, right? Otherwise, if you are creating a wave file for just CD quality, right? So then 44,100 would be good option. And then like 44,056, it is another sampling rate used in audio industry. And then so we have some sampling rates less than that in different applications, as I told you. Like in telephones, usually, like they use low sampling rate, like 8,000. So that means the number of like the quality and the frequency bandwidth means the range of frequencies that can be represented in this case would be very low, right? So we have two things, as I told you, sampling rate and bit depth, right? So bit depth, or so it is the number of bits per one sample, right? So sampling rate is number of samples per second. Bit depth is the number of bits for one sample, right? To represent one sample, how many bits are allocated, right? Usually like 16-bit would be standard bit depth, but in some cases 24 bits can be used, and even like 32 bits would be used in some cases. So you can select based on your application, your situation, right? So audio, digital audio processing, right? So we record audio, and then we do many things on those audio, right? So this software that we are using, they provide almost all the facilities to do various operations on those audio. Like we can trim, like very basic operations like trimming, splicing, and then volume adjustments, right? And then like frequency adjustments. So many different operations. Like so I will show some of those operations, and then like while this course is So advancing, so you can identify many other operations that you can do on these things on audio, right? So while this audio processing is discussed, so I'll give just one additional information there. Like so, usually the audio, right? Audio is represented with time, right? So we have time and we have amplitude, right? So with the amplitude, we can decide the loudness and things, right? So, and then like, so usually like I will draw it as a continuous signal, but actually as you know, so those are like this, those are samples, those are samples, right? Like so we with the time how amplitude is changed, right? And like, so if we take, so if we see this signal, so we can identify the frequency by looking at, right? But actually so this is the regular representation of sound with time. We call it time domain signal. Time domain signal. Time domain. But actually, in some cases, so if you are analyzing, if you want to analyze, for example, the concepts like pitch, or pitch is related to frequency. Right? If you want to analyze pitch or frequency of that sound, so then with time domain signal, it is very, very difficult to do that. Right? So in many applications, like for example, like speech analysis or music processing, and any other sound related, so most of the sound related analysis, right? We usually do that, something like time domain signal is converted into frequency domain. So I'm telling this here, like this is something additional because I'm telling this here, so most of the research, right, that like some of you may be getting to some research in your final year. You have to do a research, group research. Like for example, your senior batches, so they did some research on audio, like speech analysis. So there was one group last time, they did speech analysis and then the music processing. So last year there was one group. And then this year, speech analysis, actually there were two groups, like speech analysis, one group, music analysis. This year, there's a one group who's doing music processing. Right? Likewise, like if you select audio related projects, you may find this, like if you do speech or music, like with time domain, it's not enough. Like you may have to convert it into frequency domain. Right? So this in frequency domain, like time domain signal, I already showed you, right? So in frequency domain, what we can see is, so we have frequency in x-axis. And then again, this one would be amplitude actually, right? But it doesn't matter actually in such cases, but what we see in frequency domain would be, we will have all the frequencies that we which are available in our audio signal or our sound signal, or in this case audio signal, right? Usually for example 0 to 20,000, our audible range, right? If we consider them, yeah. So then, like they have like frequency, right? So multiple frequencies are in the signal. Multiple frequencies are in the signal, right? So those multiple frequencies would be their power, right? So for example, if we have 440, right? So there's another signal, 880. So likewise, so we have frequencies. How frequencies are distributed and their power, right? Some frequencies are 0, right? Most of the frequencies are 0, but several frequencies are having these kind of values. So this is called frequency domain. Sometimes we call frequency spectrum. How frequencies are dominate in that signal, right? Which frequencies are dominating, which frequencies are not so dominant, and which frequencies are not available, right? Some frequencies are 0. Right? That means that frequency is not there. So based on these frequencies, we can identify, sometimes we can identify the dominating pitch in this pitch or picture, right? Like multiple notes would be there, right? Like we can identify those, right? So usually what we do is, like if we have time domain signal, right? If you have time domain signal, like it is a set of values, could be its minus values as well, right? Like sampling, like time domain signal. So we cut this signal into parts, right? I will use a different color here. Right? Cut this into parts. So this one part would be It depends on the application. It could be, for example, 50 milliseconds, right? Suppose it is 50 milliseconds. I take only this part. This has maybe several samples. So then what I do is I convert this part into frequency domain. Frequency domain. So then I can identify dominating frequencies during this time, during this 50 milliseconds. And then the next 50 milliseconds, again, I convert it into frequency domain. I check the frequencies there. So it could be the same frequencies or it could be different frequencies, right? So likewise, so we cut our audio piece into parts. Sometimes it could be very small parts, sometimes it could be more than that. It could be like 200 milliseconds. So somehow, like relatively, those are smaller parts, right? So we separate the time domain signal into parts, and then each part is converted into frequency domain. Right? Can අපි දැන් මේ music වගේ ඒවා analyze කරද්දී අපි කරන එක technique එකක් තමයි මේක. Right? ඒ කියන්නේ දැන් සාමාන්‍යයෙන් අපි music එකක් අපි මේව කරලා ඒකේ pitch එක වගේ දේවල් එක්ක අපි වැඩ කරන්න ඕන කියලා හිතන්න. දැන් අපි pitch එක ඒ වගේ දේවල් එක්ක ගොඩක් වෙලාවට වැඩ කරන්න ඕන speech signal processing වගේ ඒවා කරද්දී උනත් pitch එකත් එක්ක අපිට වැඩ කරන්න වෙනවා. ඒ වගේ වෙලාවට අපි කරන එකක් තමයි ප්‍රධාන එකක් තමයි අපි මේක මේ කඩා ගන්නවා. මේ අපි දැන් sound signal එක අපි හිතමු අපි සින්දුවක් කියලා ගමු. මොකද මේ සින්දුවක් නම් ඒ සින්දුව අපි හිතමු විනාඩි 3ක් යනවා කියලා. ඒ විනාඩි 3 මේ යන්නේ අපි කැලේ වලට කඩා ගන්නවා. මේ මිලිසෙකන්ඩ්ස් 50 මිලිසෙකන්ඩ් 100 ඒ වගේ මේ අපිට මේ මොකක් හරි එහෙම ගානක් දෙන්න පුළුවන්. එහෙම කඩාගෙන ඒ එක එක කැල වෙනම අරගෙන ඒ samples ටික අරගෙන ඒ samples ටිකෙන් frequency domain එකේ ඇඳ ගන්නවා frequency spectrum එක. ඒ frequency spectrum එක බලලා අපිට ගොඩක් දේවල් decide කරන්න පුළුවන් ඒකෙන්. හරි. ඒ frequency spectrum එක මේක සාමාන්‍ය මේකට පාවිච්චි කරන techniques ගොඩක් තියෙනවා. So we use several techniques for this processor. So one is FFT, right? Fast Fourier transformation. Fast Fourier transform, right? FFT, fast Fourier transform. Fourier transform. FFT is one method, like so for example, like if you use a Python, so they have libraries to do FFT, so we can get a signal, like signal, it is an array of values, so we can take divide that array into parts, and we can take one part and we can call FFT method or function. So then it will generate the frequency spectrum, a set of values. So an array of values that we can analyze. We can analyze them using some techniques. So this is very, very basic technique that we use in no, not basic actually, it is an advanced technique that we used in audio analysis, right? So if you are doing projects in futures, like you'd come to this place, and then so that's why I additionally explain these things, right? So FFT is one approach, most famous approach, but so there are some other approaches as well. So based on the application, we have to decide. Right? So frequency domain and time domain. So there's a difference. Huh? So digital audio processing. So so if I mean so there are the software that we are using, right? We are going to use. They have these functionalities. They definitely they use those functionalities, and we can use them. So, however, if you need to do something beyond that, right? So in a research, what we do is we are doing something beyond what is existing. Right? දැන් දැනට තියෙන දේට අමතරව අලුත් දෙයක් කරන්න හදන්නේ. එතකොට ඒ වගේ වෙලාවට අර ලෙවල් එකට අපිට යන්න වෙනවා. ඒකයි මම මේ පොඩි කතාවක් එක කිව්වේ මේ මේක මේ කොයි විදිහටද කරන්න කියලා. Again, so there are steps, right? So there are several steps, like when you convert frequency time domain signal into frequency domain. So I'm not going to explain them in detail because this is something additional, but just to have an idea, right? In most of the speech processing or music processing, so this is one necessary step. One essential step, like using in most of the cases FFT, using FFT convert time domain into frequency domain. Right, and then so digital audio noise, right? So noise is what, so in any recording, there would be noise, right? So in that case, signal to noise ratio. Signal means actually the useful part of the signal. And the noise is what is not necessary, right? Noise. So signal to noise ratio is one measure that we can use to identify the quality of the sound that we have, right? Power of signal divided by power of noise power, like this. And then the audio file formats. So basically uncompressed or without compressing. If we take the original recording as it is, right? So if we can record all the information, right? So maintain full information of the recording. So those are uncompressed, right? So usually WAV files or AIFF files are the main types of uncompressed file form. And then compressed. Even in compressed, so we can, the size of the uncompressed files are obviously higher, right? So then so when we want to exchange our music, or if you want to download some music, and then if you want to email, right? Like so, for example, the WAV file would be the size would be very high, so you cannot directly email it on, for example, like in Gmail. Right? Gmail, they have the file size, the maximum file size that you can attach. Right? You cannot attach most of the WAV files. Right? In that case, to exchange, to download, and to make them available easily download. So we use compressed file formats, like MP3 is the most the popular format, and then OGG is another popular format. So if you compare these two, maybe like OGG would be the quality of OGG would be a bit higher than MP3. So likewise, in these cases, the file size would be reduced, right? So when we transfer them, so that would be easy. Like file size would be very, very lower than the uncompressed ones, right? So this in compression, so there are several concepts like lossless and lossy compression. So even in compression, the quality of uncompressed audio equals the quality of the original audio files. That means the quality would be preserved anyway in lossless. Lossy compression. So for example, like MP3 is lossy compression method. The quality of the sound would be not as the same as the original audio, uncompressed audio. Right? If you convert a WAV file into MP3 file, so you can directly you can check the quality. So you will find they are different, right? Okay, right. So like so audio files. So we talked about audio files up to now, right? So all these are audio files, right? So MP3, so they are still audio files, like compressed audio files, right? So if you take WAV file, it is audio, right? Audio file means there are samples, right? Samples are there, right? But when it comes to MIDI, this is a different way of representing audio. It's mainly in computers and related devices, right? So MIDI. So MIDI is not audio, right? So remember, MIDI is not audio. audio නෙවෙයි. audio නෙවෙයි. MIDI කියලා කියන්නේ audio නෙවෙයි. ඒ කියන්නේ MIDI ෆයිල් එකක් කියලා කියන්නේ කවුරු හරි කොහේ හරි රෙකෝඩ් කරපු මියුසික් එකක් නෙවෙයි. It's not recorded by someone and like it is not that. Audio නෙවෙයි ඇත්ත. It is not audio actually. So can anyone, okay, so Akalanka is here. So Akalanka, so in MIDI files, what do you have actually? So what do we have in MIDI files?
I didn't get the question, sir.
Yeah, so in MIDI files,
Yeah.
so I'm pretty sure you have worked with MIDI files, right? Yeah, MIDI files or MIDI devices, like there are many things. So in so if you have a MIDI file, right? So what is there?
It is only a signal, sir.
Mhm.
Yes.
If you take audio file, yeah, if you take audio file, yeah, it is a signal. Like we have samples, right? We have samples, like I mean, set of values. But in MIDI files, what do they have, and what is the difference?
Actually, sir, in my knowledge, MIDI has no any content. That's only a signal. If
Mhm.
we can, like, we can use it as is when we can save MIDI file, we can use it to play with any instrument, any kind of instrument. Just signal.
Mhm.
We can give it as an input for any. It's like a general signal that we can give to generate a particular sound. It has
Yeah.
no any content without only signal.
Yeah. So I am taking. So you said no content, right? No content. So that's. I mean, I agree, and I'll explain what does that mean. And then you said it is just a signal, right? You said it is just a signal. Actually, MIDI is not. It is not considered as signal, right? So maybe because of like the using words to explain, right? Like I got the idea. Like I mean, I understood that you know what is MIDI, right? Like you have the idea, but when you're using the words, so that's the confusion here. It is not a signal, right? So we cannot say it is a signal. So that's one thing I have to add. And then you said like MIDI file can be used to play music. Yes, exactly, right? So MIDI file has information to play a music.
Yeah.
Right. So so MIDI file actually it is set of commands.
Yeah.
I would say set of commands to generate a music, right? So like audio files, they have like so if we take audio files, so they have it is a signal. Actually it is a signal. So the values are there, right? So values are there, right? Without any other devices or anything. So if we play this, right? If we play this, so then the music would be, I mean, it would be, so we can listen that. We can listen this audio file, right? But MIDI, right? It is set of commands, actually set of commands using special device, right? Using special device, we can generate like. So we have set of commands, right? So I'll draw them in a different color here. So set of commands. Right? Set of commands to generate sounds. So MIDI file is not sound itself; it's a set of commands. So if we have a special device, for example, MIDI synthesizer. MIDI synthesizer, in most of our audio software that we are using, like for example, so if you are playing your music in your computer, if you play music using like so any software that you are playing music, right? So they have MIDI synthesizers, right? MIDI synthesizers there, right? So if you give MP3 file or WAV file or MIDI file, it will be played, right? So however, audio file is directly played, but MIDI files are played through MIDI synthesizer. So these commands would be understood by MIDI synthesizer, and then based on those commands, sound is generated. Sound is generated. Sound is generated here, right? Sound is not there in the MIDI file. But if we take audio files, sound is there. Sound signal is there. Sound signal's representation is there. So that's the difference, right? Again, audio file එක ගත්තොත් audio file එකේ අපි දැන් අර දැන් අපි මොකක්ද sound signal එකක් තියෙනවනේ. ඒ sound signal එකේ representation එකක් එතන තියෙනවා. audio file එකේ. හැබැයි MIDI file එකේ sound file එක representation එක නෙවෙයි තියෙන්නේ. ඒකේ තියෙන්නේ command set එකක්. ඇත්ත. command set එකක් තියෙන්නේ. එතකොට මේ sound එක generate කරන්න නම් ඒක MIDI synthesizer එකක් through යවන්න ඕනේ. එතකොට තමයි sound එක generate වෙන්නේ. Right? So that's a difference. Right? So we have mainly two types of files: audio files, MIDI files. Like when we work with audio, right? Like when we do audio production, so with digital technologies, so we have two types, two file types: audio and MIDI. Right? So audio, it is a representation of it is a representation of a audio signal, right? MIDI is not a direct representation of audio signal. It is a set of commands. So ඒකේ තියෙන්නේ මෙන්න මේ time එකේදී මෙන්න මේ note එක play කරන්න. මෙන්න මේ time එකේදී මෙන්න මේ note එක play කරන්න. මෙන්න මෙච්චර velocity එකකින් play කරන්න. අනේ විදිහ commands ටික තියෙනවා. කරන්න ඕනේ දේවල් අර instructions ටික තියෙනවා. So MIDI file is like a program. Like when we are writing a computer program, so we are giving instructions. So MIDI file is something like that. It is a set of instructions, right? So let's go with this, with the description here. So I have given very small description, but anyway, like when we are working with files and everything, like we can discuss these concepts more, right? Right. So music instrument digital interface. MIDI means musical instrument digital interface. Is a protocol. It is a protocol, right? That enables computer synthesizers, keyboards, and other music devices to communicate with each other. It's a communication protocol, actually, right? So if we create a MIDI file, there's a standard, right? If I have a MIDI file, so all the MIDI devices, right, they know how to play it, right? So that's why it is a standard set of rules, a protocol, right? So those are there. The specification originates in paper. So this paper, it is very important paper in music, like computer music area. It is one of the important papers. Universal Synthesizer Interface. That's the paper by these two guys from Sequential Circuits. That's the company or the institute that they worked at the time, on 1981, right? 1981 is a very important year in that sense, and it was represented in Audio Engineering Society conference in New York City, right? So from there, like we are using MIDI technology in audio production, so music production, computer music. So it allows electronic instruments and other digital musical tools to communicate via MIDI messages. We call them MIDI messages, right? So in a MIDI file contains MIDI messages, right? Actually, like using a computer program, we can, we don't need a computer program. Like there are software that we can check those MIDI messages, actually, right? We can see those MIDI messages, and then actually, like so that in most of the programming languages, they provide tools to work with MIDI files. We can do MIDI programming. So it's called MIDI programming. So you with different language, like for example Java, C#, so they provide libraries to work with MIDI, right? So MIDI itself does not make sound, right? So this is important. Huh? MIDI itself does not make sound. The audio, if you take audio file, it makes sounds. The sound signal is there, but MIDI cannot make sound. It can make sound through MIDI synthesizer, special device, so special software that can understand MIDI messages. And based on those MIDI messages, they can make sound. It is just a series of messages such as note on, note off, note number, tempo. Right? The note on velada, note off velada, note number එක මොකක්ද? So note numbers are like, if you take MIDI, so usually every MIDI information, usually they use like, like 8 bits. Eight, yeah, 8 bits or 7 bits, right? For example, like our note could be 0, 1, 2, and so on, right? And then it goes up to 1, 2, 7, 1 to 7. So these are note numbers, right? So those MIDI, so those are these numbers, they represent the notes on a piano keyboard. Piano keyboard එකේ වම් පැත්තේ ඉඳන් දකුණු පැත්තට එනකල් ඒ keys තමයි මෙතනින් represent කරන්නේ. අතන ඊට වඩා තියෙනවා මෙතන. හරි. එතකොට මේකේ so I don't remember exactly which number is for middle C note, right? So you can check. I don't remember that number, but there's a particular number. So that's middle C. So likewise, එක note වලට මේ numbers තියෙනවා. Keyboard එකේ තියෙන notes වලට තියෙන number. So then, if you give that number, that note would be played, right? So likewise, so MIDI file is a set of instructions, MIDI messages. We call MIDI messages. The instructions will have MIDI messages. So these are few, but there are many other things like about tempo and many other information are there in a MIDI as MIDI messages. A single MIDI link through a MIDI cable can carry up to 16 channels of information. So, so MIDI cable, like MIDI cable එකක් through මේ අපිට අරන් යන්න පුළුවන් 16 channels information. 16 channels කියලා කියන්නේ අපිට මේ අපි හිතමු දැන් instruments එකක information එකකින් අරන් යනවා කියලා අන්න ඒ විදිහට 16 channels 16ක information මේ MIDI cable එකක් through අරන් යන්න පුළුවන්. Right? So this could be 16 different digital instruments, for example, right? MIDI carries event messages, right? So MIDI has events actually, right? So the first MIDI event, second MIDI events, likewise, that MIDI information is there, right? Data that specify the instructions for music, including notes, notation, pitch, velocity, which is heard typically loudness or softness of volume. The volume එක වැඩිද අඩුද? ඒක velocity එකකින්. ඊට පස්සේ vibrato. Then panning to right or left of stereo. Right. දැන් සාමාන්‍ය අපි stereo කියන්නේ අපි මේ දැන් මේ headphone එකේ දැන් මේ දෙපැත්තට එන music කියන්නේ වම් පැත්තේ එකට දෙන්න දකුණු පැත්තකට දෙන්න. ඒ සාමාන්‍ය දෙකටම එනවනේ. ඒතර ඒක අපිට වෙනස් කරන්න පුළුවන්. ඒ එක පැත්තකට බාර වෙන්න. And then clock signals, right? That means the tempo, right? Right. So those information. So if we take one event, we can provide different information. So based on those information, that music is generated. ඒ කියන්නේ දැන් MIDI කියලා කියන්නේ හරියට නිකන් අර sheet music එක වගේ. ඒ කියන්නේ අතර මියුසික් එකක් නෑ. හැබැයි මියුසික් එක ජෙනරේට් කරන්න ඕනේ සියලුම ඉන්ෆර්මේෂන් එතන තියෙනවා. So we have all the information to generate that music. එතකොට දැන් sheet music එකක් දැන් උදාහරණයක් විදිහට sheet music එහෙම කියවන්න බැරි. දැන් උදාහරණයක් විදිහට මට එහෙම sheet music කියවන්න බෑ. ඒතර මට දුන්නොත් එහෙම මට ඒක මෙලෝ දෙයක් ඒක මේ පොඩි අවබෝධයක් තියෙනවා මෙන්න මේ වගේ මේ මෙතන මේක මෙන්න කියලා එහෙම පොඩි අවබෝධයක් තියෙනවා. හැබැයි සාමාන්‍ය මට ඒක බෑ. ඊට පස්සේ මට ඒක ප්ලේ කරන්නත් බෑ. මම කියන්නේ මියුසික් මියුසිෂියන් කෙනෙක් නෙවෙයි. ඒතකොට දැන් මට එහෙම එකක් දුන්නට වැඩක් නැහැ. ඒ වගේම තමයි මේ MIDI ෆයිල් එකක් අර ඒ MIDI සින්තසයිස් එකක් නෝන නිකන් එකකට දුන්නට ඒක තේරෙන්නේ නැහැ මොකද්ද මේක. හැබැයි MIDI සින්තසයිස් එක දන්නවා මේක මෙන්න මේ විදිහට තමයි ප්ලේ කරන්නේ. ඒ වගේම තමයි ෂීට් මියුසික් එක දුන්නාම ෂීට් මියුසිෂියන් දන්නවා මෙන්න මේක මෙන්න මේ නෝට් එක මේ විදිහට ප්ලේ කරන්න ඕනේ. මෙන්න මේකයි මේකේ මේක ටයිම් එක මෙන්න මෙච්චර වෙලාවක් මේ එක ප්ලේ කරන්න ඕනේ. අන්න ඒ විදිහට ඒ දන්නවා මේ මියුසිෂියන් ඒ ෂීට් මියුසික් එක දැක්කා. ඉතින් MIDI කියලා කියන්නේ එහෙම ෂීට් මියුසික් එකක් වගේ. හරි. When a musician plays MIDI instrument, all of the key presses, button presses, knob turns, and slider changes are converted into MIDI data. Right? So if you, so we have MIDI file, MIDI synthesizer, generate the music. Right? Not only music but sound, basically audio, right? Like if you have a MIDI file, MIDI synthesizer, MIDI synthesizer generate sound or the audio, right? Similarly, so we have MIDI instruments as well. MIDI instruments, right? So if you want to play keyboard, right? If you like MIDI, if you have a MIDI keyboard, not just a regular piano, but like modern keyboard, right? So then, if it has MIDI capabilities, you can generate a MIDI file using what you play. So if you play MIDI instrument, all those information would be converted into MIDI instructions or MIDI messages. The MIDI file would be generated using those information. Can MIDI file එකක් තියෙනවා නම් මේක මේව කරන්නත් පුළුවන් MIDI file instrument එකකින් MIDI file එකක් generate කරගන්නත් පුළුවන් ඒක MIDI instrument එකක් නම්, right? Or similarly we can අපිට මේ අතින් ලියන්නත් පුළුවන් ඕන MIDI file. ඒ information දාලා අතින් ලියන්නත් පුළුවන්. So when we are using for example, if you are using like Cakewalk or any other DAW software, so you can write some parts using MIDI. Right? Generate කරන්න පුළුවන් මේ notes, අදාළ notes අපිට generate කරන්න පුළුවන් ඒ අපිට මේ ඕනේ විදිහට. Right? So that's the difference between audio and MIDI. Right? Okay, so that's the end of these slides, right? So if you have any question regarding this I think I explained Nyquist-Shannon sampling theorem, I think, right? So in that case, so if I ask a question, right, like suppose if I have 8,000 sampling rate. Sampling rate 8000 hertz. So what is the frequency range that we can represent or we can use in this signal? Frequency මොන range එකේ frequency ද අපිට මේ sampling rate එක 8000යි 8000 hertz. එතකොට මොන frequencies ද අපිට පාවිච්චි කරන්න පුළුවන් වෙන්නේ මේ signal එක. මොකද මම signal එකක් කියන්නේ audio එකක් මේ digital audio එකක් generate කරනවා කියලා හිතන්න මෙන්න මේ sampling rate එකේ. එතකොට මොන frequencies ද මට පාවිච්චි කරන්න පුළුවන් මොන ඕනම frequency එකක් පාවිච්චි කරන්න බෑ. ඒතර මට පාවිච්චි කරන්න පුළුවන් range එකක් තියෙනවා. ඒ range එක මොකක්ද? වැඩිම maximum frequency that I can use. අඩේ කියන්න පුළුවන්ද?
Frequency is 4000.
Yeah, yes. 4000 hertz would be the maximum frequency that we can have. So that's what this theorem states, right? Like for lossless digitization, the sampling rate should be at least twice the maximum frequency responses. So the maximum frequency එක වගේ දෙගුණයක්. අඩුම ගානේ දෙගුණයක්. ඊට වඩා වැඩි වුණාට ප්‍රශ්නයක් නැහැ. දෙගුණයක් වෙන්න ඕනේ sampling rate එක. So maximum frequency එක කියන්නේ මේකෙදී අපිට represent කරන්න පුළුවන් මේ 4000 වෙනකම්. එතකොට අපි ගත්තොත් බිඳුවේ ඉඳලා 4000ට යනකම් ඒවල් මේකේ represent කරන්න පුළුවන්. Right? So that's why so usually when we talk, right? So when we talk in our usual talking, the frequencies would be between these two, that 0 and 4000. Again, මේ අතර තමයි අපි සාමාන්‍ය අපි කතා කරන දේවල් එහෙම තියෙන්නේ මෙන්න මේ range එක. කතා කරන. හරි. එතකොට මෙන්න මේ frequencies ටික සාමාන්‍ය ටෙලිෆෝන් conversation වලදී මෙන්න මේක ඇති. This is enough for regular telephone conversation. But if we take music and other sensitive information, right? So in that case, in such audios, like we use this. So in this case, the maximum frequency that we can use would be this is the sampling rate. The maximum frequency would be this. So that means, so generally, so our audible range can be represented here. So that's why in CD, again, CD quality, they use much higher frequency sampling rate, much higher sampling rate. Again, මේකෙදී තප්පරයකට sample 8000යි තියෙන්නේ. මේකෙදී තප්පරයකට sample 44100. So if we take maybe I explained last week, like 3 minutes song, right? If you take like in CD quality wave file, if you record wave files, how many samples would be there? In 1 second, this much, right? තප්පරයකට මෙච්චර samples ගන්න තියෙනවා. එතකොට තප්පර 60යි විනාඩි 3. Right? This much samples would be there. විනාඩි 3ක මෙන්න මෙච්චර samples ගණක් තියෙන්න පුළුවන්. විනාඩි 3ක music එකක් ගත්තොත්. ඒතර time එකත් එක්ක මෙන්න මෙච්චර samples ගණක් තියෙනවා. සින්දුවම මේ විදිහට අපි represent කරොත් මෙහෙම මේ විදිහට මේ samples මෙන්න මෙච්චර ගණක් තියෙනවා. 60 වැඩි කිව්ව 3 අන්තිම sample එක මෙතන. So when we convert them into frequency domain, as I told you, we cut that into parts, right? We call windows, right? If we cut that into like 20, like let's say 50 millisecond windows, මේ තප්පරයකදී එන්න මෙච්චර 50ක්. ඒතර මේ මිලිසෙකන්ඩ් මෙන්න මේ වගේ අපි ගත්තොත් තප්පරයකදී මෙන්න මෙච්චර ගාණක් තියෙනවා. එතකොට මෙන්න මේ එක වින්ඩෝ එකකට අයිති වෙන්නේ මෙන්න මේ එකෙන් 20න් එකක් විතර ප්‍රමාණයක්. අර මම කලින් කිව්වේ අර මේ අපි අර ෆ්‍රීකවන්සි ඩොමේන් එකට කන්වර්ට් කරනවා. එතකොට අන්න ඒ විදිහට ඒ කන්වර්ට් කරද්දී එක වින්ඩෝ එකකට කොච්චර අහු වෙනවද කියලා බලන්න. samples කීයක් තියෙනවද. Likewise. So we can do many things with these numbers actually, right? Right. Okay. So any other questions? So I'm just explaining things. Right. Okay. So